Okay, so now to liquids. Liquids do have a bit of flow. They can flow past one another because they're not stuck in their specific shapes. What do you think about their kinetic energy? Slightly more, right? Because the kinetic energy refers to energy of motion. So this one has more kinetic energy than the solid does because they can actually move. They are mobile atoms. They can flow past one another, take the shape of their container, no set shape. Temperature, what happens to a liquid whenever you heat it? So increased temperature should. So boiling is a phase change from what to what? Liquid to gas. So it should turn to gas. It should evaporate is what you call that. Okay? There is a little bit of thermal expansion with that one too, but not as much. The pressure, increasing pressure on a liquid, if you push so much on a liquid, what could you do to it? You could force those particles to touch each other and become a solid. So solids look like this. They're very, very constricted in the way they are arranged. Liquids have a little bit more freedom. So there's space between them that you could push them together some more if you apply enough pressure, but it's a lot of pressure. Like if you put enough pressure on water, it will turn to ice. Okay, it's got to be in a closed container. So it could solidify. Okay, and then gases. Let me draw gas real fast. I get your question. Gases. Okay, they have a lot of space between them. So if you put pressure on a gas, what could happen? Increased pressure of a gas. Okay, it could revert back to the liquid, or you could just say, what's going to happen to its volume? So here's my box of gas. It could go severely decrease, really decrease that volume. Okay, so that's an inverse relationship. Usually on a gas, if you have increased pressure so much, it's going to severely decrease the volume. Temperature, if you increase the temperature on a gas, what do you think it's going to do? It can't undergo a phase change, right? But that's increasing the temperature, and that's actually going to less energy. So gases are moving around us right now, right? They're moving at a certain speed. They're moving to a certain speed. You coming? Go back there. They're moving at a certain speed. I can actually make them move faster if I add more temperature, okay? So I can make them move faster, and we'll get into the details of how we measure the rate that they move. Another thing to note here as you go through these phases, as you go from solid to liquid to gas, the attractive forces are weaker. Solids have a really strong attraction. Gases have virtually no attraction for one another. And that kind of makes sense because solids, they have no choice. They're like, hey, buddy, we're next to each other. We have to be attracted to one another. If not, we're not going to be a solid anymore. And if you were trying to melt from solid to liquid or evaporate from liquid to gas, there's a certain amount of energy you have to apply. Like when does water boil? 100 degrees Celsius, right? So we have to apply that much heat so it will boil. So there's a certain amount of attraction that we have to overcome with that heat energy. No? I don't know if you had your hand up. Okay. Works for me. All right, this is the part I like. So these are the phase changes, and we talked about them, and now we need to figure out, is it endothermic or is it exothermic? Okay? So first, this is not in your paper. I want to jot down a couple of these.
Who's one in the back of it?
Sure, that's your paper. Here's your one with it. Okay, I'm leaving it on the desk because I don't want to take it. So states of matter are kind of relative to the temperature or the pressure that we exist in, or wherever it's existing. If I change the temperature or pressure, I can cause the phase to change. It can cause a state change. So I can control that. But we also have to talk about, if I add energy, which way is it going to go? Is it going to go from solid to liquid or liquid to solid? So you just got to think about the energy. Is energy needed or is energy released? And that's what we're going to label when we do these phase changes. So the way I like to do this is label the amount of kinetic energy like I did on the first chart. Solids, do they have a lot, a little, or medium energy? Kinetic energy. They have a little kinetic energy, right? Little kinetic energy. Liquids have, right, so I'm going to put medium kinetic energy. How do I increase the kinetic energy? I have to add kinetic energy, right? Add heat. So if I'm adding heat, is that endothermic or exothermic? Endothermic, definitely. That's because I have to add energy here for it to work. Solids don't just say, hey, I think I want to go to liquid. They have to be encouraged to go to liquid by adding some extra heat to them. Yeah.
I feel dumb, but what are the X?
They're just random generic letters to represent anything I want to talk about. All right, so if I'm going from more kinetic energy in the liquid to less kinetic energy in the solid, where's energy here? Is it on the reactant side or product side? I heard it. You're right. What did you say? You said the product side, right? So if I have more kinetic energy and then I have less, the energy is neither created nor destroyed. So it still has to be there someplace. In this side, it has to be as a product. Because this energy here has to equal all the energy over here. So if I have more kinetic energy and I have this little bit plus the energy I released, that should add up to that. So that was the same thing in the first one. A little kinetic energy plus that extra energy will equal that more kinetic energy. Energy is equal on both sides because I can't create or destroy it. So if it's released here, what does that mean? Exothermic, right. The word that we use to describe the energy needed to melt or freeze, which the second example is freezing. You know, it's going from liquid to solid is freezing, yes? That's freeze. Is called enthalpy of fusion, also known as H-fuzz. Delta H fuzz. Fusion means to melt, by the way. So don't think of fusion as like, I don't know, the car or nuclear fusion. Think of it as melting. And it's very specific in the way that we write it. It's the energy needed to melt or freeze 1 mole of substance X. So when I write this as a fraction, it's now a new conversion factor. Delta H is equal to energy, usually in kilojoules, per 1 mole of that substance. So for water, this is 6.01 kilojoules per 1 mole of water. And that's what H of fusion is. Write that one down for water, because you're going to use it later on. So if I had 6.01 kilojoules, how many moles of water could I melt? 1. If I had 12.02 kilojoules, how many moles of water could I melt? 2. So you're just doing conversions in your head. So that was melting and freezing. Which one do you think's next? Huh? Also known as evaporation. And then what's the opposite of evaporation? Condensation. That's our next one. I see a couple people writing still. I'll let you finish that one up.
Is that equation or whatever conversion factor is only for water?
It's only for water. Next one, vaporization and condensation. This one, we're going from the same situation. We're going from a little kinetic energy to more kinetic energy because gases move more KE. So we're putting energy into or taking energy out of? What do you think? We're putting it into that, right? We have to get the little to the more kinetic energy. So you have to put energy into this liquid to force it to turn to gas. So we're putting energy into it, then it's an endothermic reaction. And that's what is this one? Evaporation is. So who sweats in here? Everybody be brave. It's not just me, right? I'm not the only one sweating. Okay. So if you sweat, the reason you do this is because your body is trying to do what for you? Why is it trying to cool you down? Okay, you're going to maintain your body temperature homeostasis. You need to get rid of that extra heat. If not, you're going to denature all your enzymes and you're going to go go on the floor. Okay, so you need to get rid of the energy. So what is the sweat doing? What's your body temperature doing to the sweat? What is your body temperature doing to the sweat? It's evaporating it, right? So the energy to cause that evaporation to occur is coming from you. So what happens is when this liquid sweat, if I can spell sweat takes in that body heat, takes in that energy, it causes the liquid to go to gas, and the gas removes that energy from you. So it makes you feel cooler. It's a cooling process, yeah.
What is heat?
Energy.
Oh, it's energy.
Mm-hmm. So the other way, if it's hot outside, the water vapor in the air, which has a lot of kinetic energy, can condense to form a liquid, which has a little bit less kinetic energy. So where's the energy at in this equation? As a product, right? So this one is getting rid of all of its pent-up kinetic energy, and to get rid of it means it has to release it. So the energy has to be out as a product, being released and exiting as a product. Because there's no other way to get from a lot to a little unless you release it. So in this one, it has to be exothermic, so that the states of matter will correlate with what we have here. Yeah.
So, endothermic means evaporation, and then exothermic means condensation.
Or condensation is exothermic.
Yes.
Evaporation is endothermic. Yes. All right. There are two words that we commonly misuse: the words evaporation and boiling. Vaporization, also, that's kind of the term I'm talking about here. Vaporization is only occurring at the surface of a liquid. So a liquid, it'll be sitting here at the top, and every now and then one of these particles goes, I'm going to be a gas today, and then one of the gas particles will bounce back into the liquid form. Only at the surface, that's an at symbol, at the surface will general vaporization occur, which is when you have a liquid that goes straight to a gas. But you can force vaporization to occur really, really, really fast, only if you can boil it. So if you have a pot of water, where does boiling start? Where's my stove? Where's the eye of the stove? Okay, why does it start at the bottom? All right, so you're heating here. You're exciting those particles so much that the liquid particles don't want to stay together anymore. They get crazy, and they form a nice bubble. That bubble starts at the bottom, it goes to the top, and then you can see it kind of like being sporadic at the top. So the bubbles start here and go up, start here and go up. Vaporization starts where? At the top. Boiling starts at the bottom. That's a common misuse of words, but just FYI, you'll see that in your vocabulary. And then this is another enthalpy term. It's H of vaporization, also known as HVAP. Same story. It's still kilojoules per mole. And for water, the specific H vaporization is 40.7 kilojoules per mole. That is its conversion factor, 40.7 kilojoules per mole. And that's 1 mole of water.
Is that only used for water?
Only used for water. Yep. So all the two numbers I told you are only for water, but you can have H vaporization for any liquid in the world. But I'm giving you a specific number. So like ammonia's vaporization might be like 20 kilojoules per mole.
Oh.
I'm giving you a number for water. Yeah.
If someone uses water and it gets like really hot and it starts bubbling, then that's vaporization. But it's not
It usually wouldn't bubble unless it was a clear container and it could heat. If anything, it would probably vaporize the top first. Okay. Good. In about 10 minutes probably. Okay. Next, vapor pressure. This will be the last thing about vapors for a second. Do not write all this down. What does the word volatile mean? Volatile. Huh? changes to what? So, okay, perfume. I wear perfume. Moonlight Path, Bath and Body Works, if you're wondering. Anybody else? All right, deodorant. Everybody's deodorant, right? Okay, thank you. So, why do we put this stuff on? To not smell bad, or to make us smell better, yeah? Okay, so the reason we put that on is so our body heat will heat up those covalent deodorant and body spray. When it heats it up, it vaporizes really easily to make us go, oh, you smell so good, girl. So you want that, and you smell good because your body heat is heating up that stuff and making it vaporize. So volatile means it vaporizes easily. That's all it means. So things that are volatile are more likely to evaporate. They vaporize easily. So you can thank chemistry for making you smell good. Okay? Thanks, chemistry. Okay, so the only molecules that are going to vaporize though are the ones with the highest kinetic energy. So this is my favorite example. Okay, who's gone to Panera recently? Soup? Yeah, soup? Okay, maybe in the winter we get soup, okay? First thing you do, you get your soup and you go blow it. Okay, why are you blowing on it? Why is it hot? What's heated though? There's no such thing as heat. There's only such things as energy. So the particles that are hot have a lot of energy, and energy burns your tongue, right? So when you, what are you doing? You're trying to take away energy. But what you're actually doing is there's a soup. Here's soup. There's like steam coming off, right? What's the steam made of?
Energy.
No. What is steam, guys? Gas. Thank you. This is gas up here. Gas has the blank energy. Highest what kind of energy? Kinetic energy. So if you have the highest kinetic energy, you are the hottest. Okay, because you've got so much energy, you will burn people. That's why you don't put your hand over boiling water, because it's hot. Okay, so the gas particles are coming off the top of the spoon. What are you doing to them when you go? You're making them go to the person's face in front of you, right? Okay, so you're blowing away those hot particles, leaving behind the cooler particles, and then you go, oh, and eat it. So what you're actually doing is you're blowing away high kinetic energy particles to cool your soup down. Yeah? Okay, thank you.
How does energy burn your tongue?
It's because it's bombarding particles of lower kinetic energy, and so it burns it because it's like a energy explosion. I'll go over burns later. Okay.
Ooh, she burnt.
No, I didn't. Okay. Yeah. Okay. Now, if I had my soup or whatever in a closed container, and I could capture those vapors would be bouncing around, right? They're hitting the sides of the container. If they're hitting the sides of the container, and I'm holding a water bottle or something, can I kind of feel the pressure pushing back on my hand if I squeeze it? Yeah. You squeezed a water bottle before, you're not like the whole like crushing it. Okay, I don't have a water bottle in front of me. So there's pressures up there that are pushing back on the opposition of your hand. So the pressure that's caused is because of the vapors bouncing off the sides of the container. So vapor pressure is equal to gases hitting the walls of container. Pressure is not really a thing. Pressure is literally a gas particle hitting the side of the container, and that's it. So when you're measuring gas, like air pressure or tire air pressure, you put the thing you do in there, and it kind of pushes back. You ever measured your air pressure, tire air pressure? Okay, that's caused by particles pushing that little slidey thing back up. I don't know the proper word for that. Okay, next, deposition sublimation is the last phase change. This is the one that does not go through liquid phase. It skips. It goes directly from solid to gas, aka air fresheners. You know those jelly-looking air fresheners? You've seen the solid air fresheners, or even like the ones the plug-ins you put in your wall, not the liquid ones. Air fresheners work this way. They go directly from solid, and then they can make you smell good. Hey, deodorant works this way too. Your deodorant, most people don't. I don't know this for sure. Solid deodorant is kind of the thing. Liquid deodorant, gel deodorant is more solid than liquid. So it goes directly from solid to gas and makes you smell good. Dry ice. Dry ice is CO2, solid, and that's solid. Solid, and it goes directly to gas as well. So dry ice, if you ever turn 18, you can go buy dry ice. Okay. You have to be 18. You can be a child forever. Don't be an adult. It's not fun. Okay, sublimation. Think about it. Think about it with me. I got very little time with you still. Solid to gas, endothermic or exothermic?
Endo.
Why endo?
Because you have to add energy to a solid.
Right, you have to add energy to that solid to make it go to gas, so endothermic. Next one is deposition. It's completely opposite. You're going from a gas to a solid. This would be like frost, outside, or dew. No, it's frost, definitely frost. So you go from gas to solid, endo or exo. Exo, because you have to release that energy that's pent up in the gas. It's got to be exothermic. You have a blacked out kind of phase diagram on your sheet. It's hard to read, but you can try or you can resketch. So in this phase diagram, it looks like a weird Y. Looks like that. Sketch with me, okay? The areas of this phase diagram are solid, liquid, and gas. Yours is hard to read. That's why I'm asking you to sketch again. Sean, you with me? This is a phase diagram. Because a phase means just a state of matter, and this is a diagram. Phase diagram. The readings on the axes here are temperature on the bottom, usually in degrees C, and pressure on the side, usually in atmospheres. What kind of atmospheres do we live at? Anybody know? We live at one atmosphere, and we are normal people, right? We're normal people, yes. What is normal, right? So normal pressure means that you live in a normal atmosphere, which in our case, for us, is 1 atmosphere. So if I ever say normal pressure or normal atmospheric pressure, you should be thinking 1 atm. Okay? So normal pressure equals 1 atmosphere. Cool? Yeah. That says a temperature, degree C. Temperature and degree C. So if I said, what is the normal boiling point of water? So at 1 atmosphere, when does water boil? 100 degrees C, right? So on this little, let me just copy this real fast. Oops. On this thing, when you're looking at 1 atmosphere, what is the phase change for boiling? Going from what to what? Liquid to gas. So you got to look for the line between liquid and gas. You go 1 atmosphere, you go over until you see the transition between liquid and gas, and that is the boiling point. Well, what's the temperature? Drop that down, and you'll see that that's the temperature listed at the bottom of the screen, the bottom of the axes. So if I said, what is a boiling point at 2 atmospheres, what would you do? So dash, 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 dash. Read. Yeah, I don't have a reading here, so I'm going to just say 150 between what you guys said. So you just have to read the graph like this. Where would condensation occur? Between what and what? Gas and liquid. So they'd be going from here to here, right? Where would melting occur? So between here and here? Where would sublimation occur? Right here, between solid to gas. Deposition? Gas to solid. Okay, with this, again, this right here is the point where all 3 phases meet. It is called the triple point. Triple point because all 3 phases meet. At that pressure and that temperature, gas, solid, and liquid can exist. So at this, whatever that pressure is, let's call it 0.5 atmospheres, and that temperature, all 3 phases can coexist. Triple point, PT point. They can coexist.
gas and ice on.
Yes, but it would be in different parts of like a beaker or something, or different parts of a chamber. That is possible. Yep, you can reach the triple point. We've reached the triple point of carbon dioxide with solid carbon dioxide. Okay, the other point here, this other upper part where you see that it just stops, like the orange and yellow kind of blend together. At that point, this is called the critical point. There's a critical temperature and pressure. The critical point is where there's no longer a distinction between a gas and a liquid. It's like a liquid. It's like a gliquid. Okay? There's no area, there's no actual phase there. It's a mixture that's indistinguishable. You can't call it a liquid, but you can't call it a gas. So at this, be quiet for a second, at this high pressure, you've got your gas, right? Dots of gas, and you're trying to squish it together into a liquid, right? But what also is present here? High temperature. So usually high temperature means the particles speed up and go crazy, right? So when they're speeding up and going crazy, they tend to expand. So it's like expand, condense, expand, condense. And so it's a fight between, is it going to be a gas or is it going to be a solid? I mean, a liquid. So that's why it's called the critical point, because at that point, there's no area of phase. It's just a liquid or a lass, like we said. Yeah.
So is that when you like go and the boiling point for
No, this is why right here though. The boiling point, so like if you were going up in the mountains, would that be high pressure or low pressure? No. Okay, when you're going up on a mountain, what's pushing on top of you? Less air. So if you're up high, less air is pushing on you, so there's less pressure on you. Air is made of gas, right? What causes pressure again? Right, the container in that case is kind of you and your lungs. So if you have less, that's my alarm. Okay, I'm gonna finish this one part here. So whenever you're up here, this is actually high pressure, so let's call this 3 atmospheres. Here's under the ocean. I'm sorry, this is under the ocean. Can't write. This is on the mountains. That's ocean. Oh yeah. And this is on the mountains. Where is the boiling point of water here? This is the mountain.
Maybe it's a little higher.
Don't worry about one episode.
It doesn't exist.
The boiling point is over. Oops, nope, it doesn't exist there. But I drew it really, really low. Let's do it a little higher. Let's do it right here. Here's a mountain. Right under here, it boils at a little under 100 degrees C. So you can boil water faster in the mountains.
Whoa.
But if you were under the ocean at like 3 atmospheres, lots of like air and water pushing on you, so lots of atmospheric pressure. If you were here, where would you boil water? 120 something. So the more pressure pushing down on you, the more you have to heat it up to push back to actually allow it to boil. Okay?
So something below that, the second black dot, that right there.
This one
Yeah. Something below that.
will go directly to sublimation. It will
So
not
it will
boil.
never reach the
Mm-mm. All right, and then I have to go because I'm doing something at the elementary school. So I'm going to tell you what you guys need to do, and then we have to go travel. So pack up for me. No, you are not. Sorry. So this has you pack up these. If there's extra papers and things on the desk, but I'll have to get some to you. Alright, you are going to the lab, and you're going to work on this diagram practice. These diagrams, the heat curves you can try, because some of it you may have seen prior to in like 8th grade or I thought 8th grade. So I want you to try them. We can finish them tomorrow, but I need you to start them for me. You are also working on problem set 13. Since you are in the PC lab, you can get online, or if you get on your phone, you can pull up problem set 13. Problem set 13 is due tomorrow. So I think it's wise to work for the last 45 minutes or so on problem set 13. The phase diagrams you'll be able to accomplish. Do you see the phase diagrams on your worksheet? They're mainly on the right-hand side. The other ones are the heat curves, and we can do that together tomorrow, but I want you to try them, okay? Okay? Alright, wait. We're in pieces. I don't want to carry peace in the hallways. Go that way. Down the U.